Hello, everyone. Welcome. Thanks for joining our diagnostic training session today. And what you're about to see is a pre-recorded training session we did over in the United States. But be assured that a lot of the material that we cover is really applicable to any automotive application. So just be aware that yes, it is a lot of North American vehicles, but they will apply a lot of the same principles apply over in the UK as well. Now, if you do have any questions, if you're watching this during the premiere, you can just leave it in the chat. We'll be monitoring live chat. If you're watching this after the premiere, then just feel free to leave a comment underneath the video and we'll get to those as we can as well. So my name is Jason Gabrenas. I'm one of Snap-on's diagnostic technical trainers. I've been in the training department since 2013, traveling around North America, helping techs and shop owners get the most out of their diagnostic equipment. Before I did that, it was a couple years as a diagnostic sales rep at Snap-on, so I had 30 different franchisees I worked with, as well as the shops that they serviced, in order to help everyone get the most out of their diagnostic needs. Then before I did that, it was 8 years at Subaru. So I worked in a dealership, and over time, I guess, just became the default diag guy in the shop. So I always ended up having the drivability problems, the intermittent problems, the weird wiring problems that would show up on those cars. And that's really where I cut my diagnostic teeth, was trying to figure out all those weird head scratcher type cars that would come into my bed. Then before that, bunch of other miscellaneous wrenching jobs. Been a little over 25 years under hood experience for me. So our topic today is ADAS fundamentals and testing. We'll take you through a nice overview of what ADAS is and how some of it works. We'll talk about different ways to calibrate the different systems, and also talk about different ways to test the components in the ADAS as well on vehicles, because we have information for that too. So first off is going to be an overview, and let's just start at the basics. Advanced Driver Assist Systems is what ADAS stands for. So Advanced Driver Assistance System. Now, these are the things that they've been putting on vehicles the last probably 15 years or so, at least now. Things like adaptive cruise control, forward collision avoidance, lane departure warning, etc. And really the design and the thought process is to make the vehicles safer. Now, will this bring us more towards where we might get those self-driving cars that everybody seems to want? Maybe. It's going to be part and parcel of it to get there, though. We're kind of in the early era of that. And that's, I think, quite a ways down the road just because of infrastructure. But anyways, yeah, this is what we're talking about, all the different collision avoidance cameras, radars, and stuff. So let's look at the front end of this Mercedes. And it has a whole lot of sensors, and this is just the front. The back is going to be very much the same, but we have like stereoscopic multi-purpose forward camera sensors used for lane detection, sign detection, pedestrian detection, and so on. Infrared night vision sensor to allow us to see further at night when it's dark out. Camera parking sensors. So there's 3 cameras that we can see around the front, and I'm sure there's more on the back as well. And that would be used more for the surround view outside of the vehicle to help with parking. Radar collision adaptive cruise control sensors. So we're usually, when we have radars on a car, we're going to have short range and long range types. So usually the long range is in the middle, and then the short ranges will be usually in the corner of the bumpers, front and or back. Well, another thing I've noticed kind of looking around over the past couple of years, usually around about the 23s and 24 or 22 and 23 model year car, I've been noticing a lot of the grill emblems been kind of maybe like smoked plastic, or not quite as shiny, not quite as metallic as they used to be. And I think a lot of that has to do with like the radars and such being behind there, just so it allows the radar to pass through the different material. I know there's times where if you put an aftermarket grill on a vehicle, whatever the radar controls, active cruise control or whatever, won't work, because it's just the wrong material and it won't let it pass through. It just kind of reflects it back in a way. So oftentimes you have to be careful when it comes to like aftermarket parts on some of these vehicles because of that. There's also ultrasonic park sensors around here. So I mean, this is probably the earliest sensor type that would have been put on a vehicle, at least from my recollection from back in the years, is we used to put these things in aftermarket at Subaru too. You drill holes in bumpers and slide those little sensors through. They're fairly simplistic. Didn't need a whole lot of processing power to do, just kind of reflecting a sound and beeping back at the driver to let you know if you're close to an obstacle. So that was probably one of the earlier ones, and then probably a backup camera around about then. And then all this other stuff came in the last decade or so. And then, of course, there's other additional sensors and ECUs and whatnot in the car, under the hood, and so on. So a pretty complex vehicle, and if that thing gets hit, it's going to probably be a pretty pricey repair because we got to fix a bunch of them. Now, the 6 main sensors that we're going to see out there in the world, that most manufacturers are going to use some, if not all of these, in multiples and combinations on vehicles now. We got the forward camera. That's usually the one up in the on the windshield. Forward radar, like I said, long and short range versions of those. Rear camera, 360 view or bird's eye view cameras. That's where it gives you the view all the way around the vehicle. Side view or blind spot monitoring, cross traffic alert. That's usually a radar somewhere in the back bumper, maybe in the front bumper as well. And then park assist, which is our ultrasonic sensors. We have really 3 main types of sensors, and then they get used in a multitude of different ways, especially the camera. The cameras get used all over. We'll get more into that in a little bit. Well, let's talk recalibration. Now, there's 3 methods of recalibrating an ADAS system, and usually it's going to need to be done after some sort of a repair. More often than not, they're not just going to go out of whack by themselves. So it's going to be, I hit something or I replaced the windshield or something like that. So we have our static recalibration, which is going to be using the scan tool with the proper software on there, which if you have a snap-on tool, you can cover the vast majority of the market. And then a targeting system, more than likely. So for camera targets and radar targets and such, you may need some extra tooling. Dynamic recalibration, however, we really don't need additional tooling. We need a scan tool with the software on it. And then we drive the car under whatever set conditions the manufacturer tells us we need to do. And then the last one, the easiest one, is going to be an initialization. So oftentimes I just hit a button on the screen, tells it to initialize itself to the vehicle. It pairs up and it's good to go. Or maybe I have to punch in a code number, or maybe the VIN or something like that needs to get entered. But the initialization requires the least amount of steps. Now, why do I need to calibrate? As I said, slightly out of whack is not good enough. So ADAS systems rely heavily on multiple imaging and sensor processors working together to provide an accurate position of where the vehicle is in relation to its surroundings. The car needs to know where it is and where things around it are. Calibration is critical in ensuring the information being processed is precise. Even a 1-degree ADAS misalignment of a radar, camera, or sensor could drastically affect the ability of the system performance designed, especially at highway speeds. So for example, if my pitch is 1 degree in one direction and 1 degree the other direction, I might be able to see further down the road, or I might not be able to see far enough down the road. So that's looking forward. Also, talk about spread left to right. So if the vehicle is not straight going down the road and I have a slight deviation, I might not pick up a car that's in front of me at a certain distance down the road. So at 160 meters distance, a 7-degree field of view is 19.5 meters across. A standard highway lane is 3.65 meters wide. So at 160 meters, this represents 1.3 degrees off. This is approximately 2.2 millimeters on an adjustment screw, because a lot of these radars and cameras, they may have an adjustment screw, a lot of radars for sure, or a bent bracket. So if I have a bracket and they're not the strongest metal these things are made out of either, sometimes I've seen them even get damaged in shipping. But if the bracket is not quite straight enough, it can be enough to throw it off. So you need to make sure everything's straight, everything's lined up. Another example from Toyota here. This is an optical axis calibration. So if I reuse the camera, or I reuse the positioning of the camera after, say, I replaced the windshield or something like that, and did not adjust it, the vehicle's going to think, well, the edge of the road is right here, and it's actually not. It's a totally different line over here. So if I can see that going down like that, the vehicle would tend to, maybe operate in a method unexpected by the driver. Let's put it that way, because it could be a bunch of different things. But there's the previous learn, and then when we do a relearn after we adjust it, there's the current axis, and it's straight on, level with the road. So even though the pictures look a little skewed too, but it is parallel or level with the road. If you don't do this, you may also get a code there: front camera module incorrect axial. So that's important to need to be able to do that. Otherwise, those systems go. So what do I need for static recalibration? As I said before, you need a scan tool with the proper software on there. Like I said, if you use a snap-on scan tool, you'll be able to cover a very large number of resets, relearns that you might need to do. I would say the vast majority of them. You also need the proper recalibration targets and the fixtures to hold those targets in the static realm, just so we have the targets up in the right spot. So here's an example on a Honda Accord doing the camera, and it needs to fire at these 3 different targets in series. To do a dynamic reset, as I said, it's a lot easier. So I hook the scan tool to the car, basically puts the car in a learning mode, and then I just drive it in whatever conditions the manufacturer says I need to drive it. We call it a target-rich environment. So it's got other vehicles, other objects that it can look at on the road. There's an example on a 2014 Cadillac SUV. It says drives faster than 35 miles an hour, 56 kilometers. Avoid extreme accel or decel. Follow 1 or more vehicles. Typical traffic is fine, but vehicles 100 to 165 feet or 30 to 50 meters away are most effective at decreasing calibration time. Drive on a straight road with many stationary objects at the side of it. Also note that every manufacturer is going to call their system something different, and that's really up to the marketing department, I guess. For example, lane departure alert. If I was going to just generically call something a lane departure, well, Ford calls it lane departure warning. Let's see, lane sense is what Jeep calls it. Sway warning is what Subaru calls it, and so on. So you see, some of them are fairly standard, but a lot of them are not. So you need to be aware of that. And even on the same manufacturer, it might be a different procedure depending on what item you're doing and also what system the vehicle needs. And that brings me to our next section, which is vehicle preconditioning best practices for ADAS calibration. So what do we need before we do an actual calibration? So that was kind of high level. Let's get a little bit deeper. So first thing you need to do before you do anything, if you even suspect that you may need to do a calibration, you want to look at the service information. You need to understand all the requirements. Static, is it a static recalibration? Is it dynamic? Is it both? Because sometimes it can be. I do a static in the bay and then I need to drive the vehicle. What is the process to complete the dynamic recalibration? Do I need to drive over 35 or do I need to drive over 50? What systems need to be recalibrated in unison? Because sometimes they need to be calibrated at the same time. Camera and radar, for example. Research TSBs for known problems or needs for reflash of the ECU, for example. Maybe there was a reset or a relearn that needed to be done. And then you can always review OEM position statements as well as when it comes to scanning and vehicle repair and such. Those are available at a website called OEM1stop.com. So it's OEM, the number 1 stop.com, and they have free access to these position statements if you want. Also note, it's going to depend, as I said, even on the vehicle you're working on. Here's an example that I dealt with. I actually filmed a video on this a little while ago, a quick tip video on a 2018 Subaru Forester. And note how it says down here, this little excerpt I took out of ShopKey. If eyesight is selected, and I'm talking about on the scan tool, if I tap the button on the scan tool to get in the eyesight system, if that is selected without pressing 2 switches at the same time, the camera adjustment items are not displayed. That'll help prevent misoperations. So if you're messing around in there and you're not supposed to be, so instead of messing something up, it's just not even going to display the option to do that. Also, the message does not display when the camera does not finish startup. So what you need to do is you need to press the pre-collision brake off switch and the lane departure warning off switch that are mounted in the cover up above, up on the roof. So you have to hold them down at the same time, then press the eyesight button, and then it will magically appear on the menu. That is not a glitch in the software. That is a function designed in there by Subaru. So if that ever happened to you, that's why it wouldn't show up on the menu. You need to read the manufacturer's instruction because that's right in there, right from the manufacturer. Works the same on the factory tool as it does on, like, say, our tool. Another example, 14 Acura NDX, right? So that's their SUV. And depending on what system they have, they both have a camera on the windshield. If it's forward collision warning and lane departure warning, then it has these 2 targets that it uses. And it's a similar procedure between the two, but it's a little bit different. Or if it has lane keep assist, it's a different target set, and it's a different procedure to do. So you would need to know what system is on that vehicle before you even get started with the system. Here's another one on Ford pickup trucks, and this is a 2015, so it's been around for a while. The tail light is integrated with a blind spot monitoring radar, so the radar and tail light are all one assembly. So if I need to replace the tail light, I need to recalibrate the radar. So if you need to replace the tail light assembly, you need to recalibrate the radar as well. It is a dynamic recalibration, so it's just driving it down the road type of thing. That'll relearn, but it still needs to be done. Once we've done that, next thing is we're already sitting in the driver's seat anyways with the key on. Let's inspect the warning lights. Make sure that what systems are available on the vehicle, because oftentimes it'll be laid out there. And then what systems are turned on and off. Document the dash condition, what lights are on or off, what the fuel level is prior, because that's important too. Documenting mileage at the beginning of the recalibration process in the case that you need to do a dynamic recalibration as well. We need to talk about curb weight, wet. The fuel level must be full because the vehicle is assuming that the weight and balance are going to be as such as I have a full tank of gas. The vehicle's fuel level sensor, especially nowadays, is going to be connected through the CAN network, and the vehicle may not allow you to calibrate unless it sees that the tank is full. Brake fluid level has to be full too. The brake fluid level sensor output can cause electronic emergency braking systems to shut down. So that's kind of a twofold statement right there. So one way is, well, if my electronic emergency brake system isn't working, is it because there's a fault in the system, or is the brake fluid too low? Other side of the coin, if I'm going to try and recalibrate the system, it needs full brake level, or at least it needs to read that brake fluid level sensor output in order to do it. Remove excess weight from the vehicle. If I got a duffel bag with free weights in the back, I need to take those out. We want to get it to the factory curb weight and drive height as it would have been rolling off the assembly. We also need to validate the wheel alignment. Before I start doing anything else, we need to validate the alignment too. So after I've already checked to see what was in the vehicle, I've read up on it first before I even touched the vehicle. Then when I got in the vehicle, I documented the dash lights and everything. Then I wanted to make sure that the vehicle is as level as I can and full and all that. And now we want to perform an alignment validation. We want to assure that the center line and the thrust line are the same. We want to understand that when the vehicle's computer is going to make corrections to the direction of the vehicle, the system has to work off of an assumption that the thrust angle is not in excess and the total tow is within the range set by the manufacturer. So some, especially newer vehicles with electronic power steering, if it sees you go out, it might try and pull you back in, but it's doing that with a force, assuming that the vehicle is going straight and square down the road. So we need to make sure the alignment is 100% correct before we do anything. It is critical. So even like we said, even half a degree on the alignment could be 50 feet down the road off in one way or the other. And everything kind of lines up, like the radar and the camera, everything lines up off the center of the vehicle. So if it's not right, you got to make sure it's right before you start. Manufacturers demand it even. So this is just a random sampling of different manufacturers. And if it's a dynamic with static preconditioning in this case, recommend an alignment check. This one, it has to be on a wheel alignment route, requires wheel alignment, etc. So depending on the manufacturer, depending on what we're trying to do, needs to either be on a rack, needs to be checked, or it needs to be actually aligned before we do anything. So you want to make sure all that happens. Then when we're going to get ready to go, we need to make sure we have a good battery charger or battery maintainer on there, because you have no idea how long that battery is going to last. The total amperage draw from the vehicle can exceed 50 amps because they have cameras and radars and modules, all sorts of different things on when this is going on. The condition of the battery in an event's been sitting for possibly weeks while at the collision shop or waiting for parts or whatever. You don't know what that battery is going to look like. Jump packs are just that. They're just used for jumping, just a short burst of power. So you don't use that as a battery maintainer. Conventional battery chargers are also not intended for that. They tend to deliver excess AC noise without the voltage and amperage at the current level. Specialized battery maintainer should be used, like the Snap-on EEBC 505 pictured here, which has a reprogramming feature that delivers clean, and consistent current and amperage at the same. I'm sure there's other ones out there. And then we need to make sure our area is clear. You may need more area in your shop than you may think or may know. Shop and lighting conditions need to be the same. Let's see, ambient lighting needs to be homogeneous. So like I said, it needs to be very even, no shadows, no hot spots. Has to be clear of contrasting area behind the targets, no bright windows behind the targets, allow adequate space in front and behind the vehicle, and clear the cameras for field of view. So we can see we got a decent amount of room right there. For example, on a 2019 Honda CR-V, it's 15 feet long. The target needs to be 20 feet from the center of the right front wheel. The required distance behind the vehicle is approximately 3 feet. So the overall distance needed from front to back, I need 38 feet, including whatever my target needs to be. So probably closer to 40 to be able to do that. Now, I do know there's folks out there that do the stuff outside and stuff like that. It can be done. It's probably more difficult to do it outside, I would imagine. Especially your lighting's probably fairly similar as long as you're doing it kind of in the middle of the day. So you don't really have to worry too much about that. But levelness and things like that, you need to worry about. As I said, the target needs to be lit evenly. So here's a couple examples. This is from Toyota. All right, it needs to be illuminated properly. This guy's got an app on his phone. It's a light meter, so it can tell, you know, how bright the light is and how much light is on the target. Might not be a bad thing. I imagine it's probably a free one out there. I don't know. I haven't looked into that one, but he's using a light meter to do that. Now, if I'm doing a static recalibration, like we said, we need to do some stuff. We might need some extra tools and such. So, and this is an example from a manufacturer, probably an Asian manufacturer, if I'm not mistaken. I found a lot of Asian manufacturers do it this way, and they need targets and stuff. A lot of European manufacturers seem to use like a lot of just recalibration. You don't really need to do a lot of the dynamic or static. And then I've also noticed in US vehicles, it's a lot of dynamic. They still might have static, but it's going to be a lot of dynamic going down the road. Special tools. In this case, it has a centering jig, and there's a plumb bob involved, and there's string, and there's tape measures and tape and all sorts of things involved. You have to make all sorts of different measurements. You have to do some math. It's a pain. It's going to take a long time to do with the string, the plumb bob, and all that. There are other ways that can be done. For example, our first ADAS kit that we came out with called the Easy ADAS. So it's just kind of a rack, but it uses lasers to center everything. So we center, we get the center line of the vehicle, and then we center the rack, the thing that holds the targets, off of that laser beam as well. So everything's kind of straight, and it's where it needs to be. Make sure it's the right distance. Even easier is electronic imaging, using it that way. For example, our TruePoint system. So that is an electronic imaging system that measures the vehicle and models the vehicle in 3D space in 6 dimensions. Allows us to check for distance and yaw and roll and pitch and all sorts of different things. And it's going to be based on the vehicle. So it uses the vehicle as the point of reference, not the floor, not, you know, any other random thing that's going on, because the floor needs to be flat. If the floor is not flat, then you might run into some concerns, and this alleviates a lot of that because of that modeling of the vehicle. It takes the vehicle, models it in a 3D space, and then it says, okay, that's flat wherever it is. And then it makes adjustments accordingly for it. It actually shows you where to position the rack. It's kind of neat, but that is the tip top of the line. So then, of course, we would want to do, I did forget to mention in here, and I noticed Billy commented on Facebook, pre and post scans too. We want to pre-scan the vehicle before it comes in, kind of when we're doing that bulb check, I guess would be a good time to do that. And then after the calibration is complete, we want to take it on a road test and then do a post test as well, plus ADAS calibration report if needed. So let's talk about the different sensors and how we can kind of test them, because they are electronic components. And believe it or not, we do have component tests available for many sensors on the vehicle. So our main 4 that we're going to talk about here is going to be radar, ultrasonic camera, and LiDAR. LiDAR is the least common out of any of these, but you'll pretty much find the other 3 on just about any vehicle. So first one's radar. Radar stands for radio detection and ranging. It transmits radio waves and then calculates how long those radio waves take to come back. And a little bit of math involved internally in the module. It knows whether a vehicle is pulling away or getting closer, staying the same distance away, and all that. So it works by radio. So front-facing radar is often used on adaptive cruise control, forward collision warning, and automatic emergency braking. That's the most common stuff, especially for the long-range stuff. For the cross-traffic alert and so on, you'd probably use a short-range radar that's kind of more out to the side. There's also rear side-facing radar sensors. Usually those are on the corners of underneath the bumper fascia in the back. And they will tell whether or not there's a vehicle inside a box behind your car that is in the blind spot. So it's going to alert you that you are in a blind, or that a vehicle is in your blind spot. You get the little LED on the mirror or what. And then also can be used if I'm backing out of a space and I can't really see and there's a car coming down the side. It'll alert me to that as well. That's oftentimes what those blind spot radar sensors are used for too. Now, if I was going to test this electrically, I can. You'll see I got power on both sides, a couple powers, and then I have ground, and then I have computer data, so CAN bus, and then I have internal CAN bus as well. On this particular vehicle, it's got left and right, and depending on what side it gets plugged into, it's either going to get power on pin 3 or it's going to get ground on pin 3, so it knows what side it's on. So that's kind of a simple way for the vehicle to know what side it's on. Ultrasonic sensors. Ultrasonic sensors are very not complicated. Transmits audio waves and calculates the return time. Like I said, it's probably one of the earlier ones that we found out there in the actually got put on people's cars. Usually used almost exclusively for parking. Parking assist and self-parking systems, because some newer vehicles have self-park systems as well, and object detection and driver notification. They're mounted on the rear or the front bumper. I've seen them on both, and they can detect an obstacle 2 to 2.5 meters away. Distance is communicated to the driver in real time using buzzers and vibrating things. If I was going to test those, like I said, they're fairly simplistic, 2 or 3 wires. If it's got a 3-wire, it's going to have a power and a ground and its own signal wire that goes back to the module. Otherwise, on a 2-wire, I think we might look at one in a little bit that it just plugs in that it's a CAN bus module. So it just plugs into the bus and there it is, and just sends the messages over CAN. Next one's camera. So there are multiple cameras on vehicles nowadays. It's not just the one in the windshield. I think just about every single car probably has one in the windshield now for a multitude of uses. But it works by turning light into electronic signals. So I have my little lens here, and the light comes in and it hits this photo sensor on the back, which then uses all this processing power to send it out as a digital signal to the vehicle. It can either be an actual video signal or it could be just data, depending on what it is. So there's multiple camera types, as I said. So probably the earliest one was going to be like your rear backup camera. So it's for object detection, also for when I'm backing up, I want to check my distance, etc. In this case, it's using a trailer tow to line the hitch up with the trailer. I would say that's very helpful as well. It's got guides on it. Next one's going to be lane centering. So use the one in the front, and it'll try and keep the vehicle centered in the lane, either passively by beeping or flashing a light or alerting the driver some other way, or actively doing it by using electronic power steering and centering the vehicle as well. Front-facing panoscopic camera would be your single point camera, used often for lane departure warning, lane keeping, automatic headlight high beam activation and dimming, so it sees the headlights coming in, knows to dim. Can use with radar to aid distance measuring as well. Can also be used for sign recognition and so on. Stereoscopic camera, not used on nearly as many vehicles as that one, but Subaru's EyeSight is the most prevalent out there with the 2 eyes. So automatic emergency braking, adaptive cruise control, lane departure warning, lane keep assist, automatic headlight high beams, and then also can measure distance. Since it is stereo, 2 eyes allows us depth perception. So 2 eyes on the car allows the car depth perception as well. Can also be used for object recognition, as I mentioned. So it can traffic signs and see vehicles and markings on the lanes and such, so it knows what is going on here. So as we can see, driving through intersections and such, it knows where the stop signs are. It knows where the stop line is. This is where we're kind of getting into approaching the realm of self-driving cars, but it's going to be way more complicated than just slapping a bunch of this stuff on there, right? So just be aware. Also, surround view. That's just a kind of a cool little system. Surround view cameras, because it's got cameras around the vehicle that point kind of at the ground and around the outside, and the software stitches them together so I can see a full spectrum of what's going around the vehicle. Also, you need way more room for that, because you see these big tarps basically that they put down for the cameras to calibrate stuff. Also useful with trailers. There's also, you may have seen from I think it was Chevy advertised it first that I saw, where you put a camera on the back of the trailer and it actually allows you to see all the way around the vehicle, including the trailer. It just has one seamless picture. It just stitches them. And then if I'm going to look at cameras, more than likely testing them, I might get power, I might get ground, but it's probably going to be a shielded one-piece type of unit. So I might need a breakout box or something like that to be able to test them, but they are still tested. And last one is LiDAR. So LiDAR works with light, lasers. So light detection and ranging, transmits light waves and calculates how long it takes to come back. And it can kind of 3D map the world. Now, a couple Audis use this. Not a lot of other manufacturers that I've seen really use LiDAR as such, more radar. I would imagine probably because it's fairly pricey. Not a lot of them around out there. They are out there, but there's not a lot of them. So it is used for adaptive cruise control, pedestrian detection, emergency braking, and such. And then once again, this can be tested too. So laser distance regulation control module right here, and it's going to have power, ground, network wires, and etc. So it can still be tested there as well. All right, let's go live on the tool here real quick. Look at a couple different vehicles that we have in there. Let's look at the Forester first. So this is that 2018 Forester. Like I said, I can't really do anything on the scan tool without pressing the buttons that I can't press because I'm not hooked up to a car. So driver aids and ADAS is the section inside Got a Component Test. And then we see a bunch of different things that we can test. So for example, like park assist, right? So the park assist sensor, that is going to be a CAN bus I mentioned earlier. So reverse automatic braking uses sonar sensors in the rear bumper of the vehicle. The sensors are similar to traditional backup sensor. Sensors send a signal to reverse automatic braking control unit via dedicated CAN. When the vehicle is backing up, the system becomes active. When the controller determines a rear collision is imminent, sends a signal eyesight stereo camera to apply the brakes. Vehicle traveling less than 9 miles an hour will stop before colliding with the object. So we have those, and like I said, it's CAN bus, so really can't be tested as such. Scan tool will be required to check for codes. Sensors can be checked for physical damage and proper installation. You could probably check a bus signal on it as well, but no power or ground or anything. Blind spot monitoring sensor. So it's going to give me the, it's got CAN bus, it's got voltage, etc. It's going to be rear corners of the vehicle behind the bumper cover. Do a DC voltage test. We want to check for power and ground. And like I said, I can't do anything with scanner on that one. So let's pull up the next one. F-150. This is the one with the blind spot monitor in the taillight. And it's going to tell us that if we go into driver aids. Blind spot monitoring module. In this case, it gives you all the information, tells you it's determining whether another vehicle is present within a blind spot. When replacing either blind spot monitoring module, programmable module installation is required. Left and right side area bumper cover needs to be clear of obstructions or for a system to work correctly. Blind spot information system and cross traffic alert cannot be turned off. And when restricted key is in use and if equipped with tow bar from the factory, that automatically turns off when there's a trailer. So that's good. I can do voltage and ground. Let's see these park assist sensors. We can do cameras. Check voltage to the cameras. There's your component information there. Let's see. Park assist sensor in this case. Oh, this one does voltage. That's a 3-wire sensor. Okay, let's go to scanner. See what we can do there. Okay, so on the F-150, we have the camera right there. So that's the image processing module. A is going to be your lane assist camera. Side obstacle detection module is going to be your blind spot monitor. In this case, only codes and data in that case. Image processing module, we have new module initialization and 360 camera calibration. So that'll do your 360 camera as well with those big mats, large target mats. So it does say you need the target mats in there. Next one's going to be this Denali. So if we go Acadia Denali, driver aids, object detection sensor, front view camera, park assist, object detection sensor, component information, side blind zone alert. It's designed to detect vehicles or other objects that may be located in the vehicle's blind spots. So it's blind spot monitor. Side object sensors are located in the end of the rear bumper on each side of the vehicle behind the bumper. And then I can do a signature test in here because it is over CAN bus. So it wants to see CAN bus activity on that. So this one actually tells you to test it via CAN bus. As far as scanner functions, I'm going here. You got a lot of different modules: active safety control module, front view camera system, for example, front view camera learn. In this case, I already did it in the demo and actually remembered that I did. So it says it's in learn mode and you need to complete the learn process. So to learn mode, you click a button on the screen, drive it down the road under whatever set conditions until it says it's complete, and then it's complete. So that's a dynamic test, not a static test. Radar sensor, how about that one? Long range sensor module confirm. Starting the learn procedure will delete learn values. You need to complete this once it's done because it's just going to wipe out what was there before. Drive the vehicle for 10 to 30 minutes or until calibration is complete. Got to be greater than 35. 30 to 50 meters away, as we said before, is going to be very similar to that cal. So that's a dynamic recalibration as well. Okay, one more. I'm going to go with this BMW. So under guided component tests, we actually can do the cameras and stuff. Actually, can do a lot of stuff. But if I wanted to do like the mirror, the camera, say the rear view camera. Right, so that is a proprietary connector. It's a 4-pin connector. Looks kind of like a S-video connector, I guess. Go through there. Make sure it's clean before you condemn the camera. And it says harness side back probe in the 4-pin connector. So you may want to check it at the control unit as well. And then scanner wise on this Beamer. Lane keep or lane change warning. That's what that one is. So there is an initialization on this one. So it's not a dynamic, it's not a static, it is an initialization. So if I replace the unit or body work in the area, I need to reinitialize it, hit continue. Control unit and slate must be adjusted independently. Correction angle of the sensors reset during the adjustment. Control unit's the right side and the left unit's on the left side. So you can choose left or right. It's adjusted in the next step. Ignition must be turned on. Do you want to start? Yes. And then it does this initialization. It takes a couple seconds and then it says it's done. Simple. So initializations are the easiest ones, like I said, and it also seems like most European-based manufacturers do it that way. A lot of Asian manufacturers do a static with a target, and domestic US vehicles seem to be kind of a mixture of both, more dynamic than any. So that is our high-level kind of ADAS discussion for today. And with that, that is our time here today. So make sure you tune in for new diagnostic content every week. We will be premiering a new video every Wednesday at 7 p.m. UK time. So make sure you check it out on the YouTube channel. If you're watching, well, of course, you would be watching this on YouTube, but make sure you subscribe, thumbs up, ring the little notification bell so you know anytime we post new content. And it's youtube.com/SnapOnDiagnosticsUK. With that, time for questions. If you have any questions, just feel free. Once again, if you're watching this on a premiere, just leave it in the live chat and we'll answer those. Otherwise, leave a comment under the video and we will get to those as we monitor those comments as well. So I'd like to thank you for taking a little bit of time out of your day to learning a little bit more about how you might be able to be more efficient at diagnosing vehicles using some of the information that we've given you today. Hopefully we'll see you next week. Hopefully you can watch and see you on any of our other videos. Have a good week, have a good night, and take care.